Hey, welcome back. Today we're taking a look at potential energy diagrams. These look like graphs and they chart the energy of a reaction as the reaction proceeds. So during a chemical reaction, two things really are happening. One, the existing bonds in the reactant, so here are my reactants, the existing bonds must be broken. So we see that here. We've got the carbon by itself and all the oxygens by themselves and all the hydrogens by themselves. So these bonds were broken. And breaking those bonds requires energy. It takes energy to split those atoms apart. The new bonds of the products then have to be formed. So step two, the new bonds have to be formed. And we see that down here. Now the oxygen is repairing up with the hydrogens, the carbon's repairing up with the oxygens, and that's the reaction taking place. We're breaking bonds and making bonds. Forming those new bonds releases energy. So we absorb energy as we break bonds, rearrange our atoms, and then release energy as we reform bonds. And that ends up with what we call potential energy diagram that looks like this. Whenever reactants, we increase the energy, so we have energy here in the y-axis, and we increase the energy as we break the bonds. You can see they're being broken there, and then we release energy as new bonds are formed, and we get our products. That initial investment of energy, so the energy you have to put in to break the bonds, and we see that as the hump here, that initial amount of energy is what we call the activation energy. And you'll almost always see it abbreviated EA, so energy of activation. The activation energy, that's the amount of energy it takes to break those initial bonds, to get us up over that hump, and then after that, the rest of it's just gravy, sliding on down. So we have two different types of reactions, endothermic and exothermic reaction. It all kind of matters what happens after the transition state. So the transition state is kind of the top of that hump when the bonds of our reactants are breaking and the bonds of our products are starting to form. We've got the intermediary transition state because it's right there in the middle as we transition from reactants to products. Anyway, the overall reaction of the overall energy of the reaction is either going to be endothermic or exothermic. Endothermic means that energy goes into the reaction. If you were to feel this reaction as it were happening, it would feel cold to the touch. You'd be absorbing energy from your hands or whatever it is you're feeling it with, and it'd be using that energy for the reaction. We can tell by looking at a potential energy diagram that it's an endothermic reaction because your products will be higher up than your reactants. So we absorb this much of energy, this amount of energy here, the activation energy, in order to get to the transition state, and then we release this much energy when we formed our new bonds for our products. That's going to be a difference of energy. We needed to absorb more energy than what we were able to release. Now, on the other hand, exothermic reactions, think of exiting, energy is going to come out of this reaction. They release more energy than what they absorb. And again, we can tell that looking at a potential energy diagram because the products are lower than the reactants. We had to use this much energy here, the activation energy, to get the reaction going, and then we released this much energy. A lot more energy was released than what we needed to get to the activation energy. So the net gain is going to be positive or negative. Technically, we're going to lose energy. Energy is going to come out of the reaction. How much energy? Well, the difference is however much is between your reactants and your products. All right, so that brings us to enzymes, the whole subject of what we're working on here in this class, in this chapter. An enzyme speeds up the reaction by lowering the activation energy barrier. So we see that here. It does not change the overall change in energy, which we symbolize delta G. So triangle is delta, it means change. G is what we use for energy. So it does not change the overall change of energy of the reaction. Our reactants are starting with this amount of energy, and our products are ending with this amount of energy. That doesn't change. We're looking at the red line, that's the enzyme catalyzed line, and the black line, that's the non-enzyme, that's the normal reaction. The difference here is still the same. So we started up on this dotted line and we ended on this dotted line. That delta G does not change. So enzymes do not give us more energy. They don't release more energy. They don't make things more energy efficient. All they do is they lower the activation energy. We see that here. That way the reaction can happen faster. Not with less energy, just easier for that reaction to happen. An analogy I always liked was this picture here of the frogs jumping over the wall. And you can think of the wall as the activation barrier. It's like the bump on the graph here. And yes, there are some frogs that can jump over it when it's all the way up, but you're going to get a lot more frogs that can jump over it faster when that wall is lowered, and it's going to be lowered because of an enzyme. So how is it that enzymes do all that? Well, often the reason why we have an activation energy is because molecules, in order to react, they have to collide. They have to bump into one another. And that takes some energy. And then here's the thing. Even if they use the energy and they bump into each other, it doesn't always just make a new reaction. Here are a couple of molecules colliding, and guess what? Nothing happens. They aren't lined up correctly. They go ahead and they flip around, they try it again, and guess what? They just rebound. The reaction does not occur. We started with a black dot and a red dot, and a blue dot and two red dots, and we ended with a black dot with a red dot and a blue dot with two red dots. We didn't have a reaction occur. For this particular reaction, these atoms, these molecules, have to be lined up in the exact right position. We see that here. Okay, unless this guy is facing this direction and this guy is facing that direction, voila, boom, there the reaction happens. This would be our transition state here, where our bonds are breaking and new bonds are forming. And voila, now we got some products. But only when it was lined up like this. These other collisions didn't happen in the correct orientation, so they didn't happen at all. That would be wasted energy. That's why the activation energy is a lot higher for a non-catalyzed reaction. You might have to try it 3, 4, 5 times before you get those atoms lined up properly. One of the ways that enzymes speed up that process, they lower the activation energy, is by lining up those atoms for us. That's why shape is so very important when it comes to enzymes. They hold on to the atoms in a very specific way, and they make sure that when they collide, they will collide how they need to. They make sure they're not going to collide like this. They're not going to collide like this. They're going to collide. They're going to run into each other when they're lined up correctly. So a lot of times enzymes are just proteins lining up molecules to make sure they collide correctly. So that is potential energy graphs for you. I know you have a homework tonight, and we'll be working on a lab tomorrow that deal with those potential energy graphs. Thanks for tuning in.